Hello everyone and welcome back. This is the second session of the 3-episode introduction of OpenFoam 12 programming. In the first session, we had the chance to take a look to define a custom viscosity power law. The approach that we showed in the previous session was generic and it's applicable to other models like the population balance breakage and coalescence kernels or drag forces. In this session, we are going to take a look to the custom boundary condition and take a look to how we can define a new boundary condition in OpenFoam 12. What is the task? The task is to define a parabolic velocity profile for a pipe flow. In this subtask, we use the location inside the geometry, which is the radial distance from the center line, and then have a fully developed velocity profile at the inlet. And then we defined a test case and test it. Then we take a look into the time varying fully developed velocity profile. We also include the time variable into the boundary condition. It's so handy in defining other formula and models for the boundary conditions. So two important parameters. The first one is the location that we take care of it in this task and the time that we take care of it in the second subtask. And then we take a look into the sinusoidal temperature variation for another test case. Also, we can take a look to sinusoidal especially varying temperature profile. It means that the sinusoidal is also depends on the location in geometry. And at the end, we will take a look for the velocity boundary condition, which is oscillatory. So 5 subtasks are defined here, and we start from the scratch for this development. Now let's get to work. Developing custom boundary conditions indeed allow users to define specific behaviors at the boundaries that are not available in the standard set of boundary conditions. Now we'll go through a systematic guide for creating a custom boundary condition template in OpenFoam by leveraging an existing boundary condition as a starting point. So if we want to start, we're going to use previously developed boundary condition like swirlInletVelocity. It doesn't matter which one you choose, indeed you should just check the codes or the concept to be as close as your own case, just like what we do in simulations of the OpenFoam and using the very close test case from tutorials. So we'll take a look into the source folder, and if you want to see where the boundary conditions are, we should go to the finite volume and then go to the fields folder, FV patch fields, because the boundary condition are defined on patch. We have basic, constraint, derived, and FV patch fields. Basically these three are the main one, and in the derived we can find many different boundary conditions like inlet, outlet, fixed mean, fixed flux pressure, coded fixed value, and so on. But what we are looking at is swirlInlet velocity. So we take a copy and then paste it into our directory. I rename it to original version, and then I made a copy of it to make the changes into it. First, let's take a look into this folder. We have two files, swirlInletVelocity FV patch vector field, and for the C and H file. I changed the name to custom BC, or let's put a more informative name on it, parabolic velocity, and change the name of the files here also, city and parabolic velocity.h. Next we should modify the files, so I open both, and here I should replace all the swirlInletVelocity with the parabolic velocity keyword. So I will put the parabolic velocity in replace and put the swirl inlet velocity in the find field, and then I replace them all. This was the C file, and let's change for the H file. Now everything has been changed from the swirl inlet velocity into the parabolic velocity. Let me do it again just to show you precisely what exactly have been done. I find all the swirl inlet velocity keywords and replace them with the parabolic velocity keyword. So let's replace them all and then save it. Just like the previous session, we go back to the drive folder and take a look for the make folder. We do not have any make folder here, so I go one step above. There is no make folder again, and it's still nothing. And here I find the make folder. So I will pick this one and paste the make folder beside these two. We have two files here. I open them. I don't need all of them, so I just scroll down to see what I have here. So I can just remove things over here. One thing worth to mention is that if you want to check where your libraries will be compiled, you can just go to your home directory, which is here, and then OpenFoam folder and go to your username -12 and platforms. Then in Linux 64 GCC dpint 32 folder, you will find the lib folder, and here you will see the library that you have already compiled, just like the lib scale out that we had in the previous session. And now we have this lib parabolic velocity.so library. When you want to include the library into your simulation, you should name it as you can see here. So let's go back to the C files. I open the C and H file again. In the C file, we have the main code, and in the H file, we have the headers. Like here, we have include some libraries. We'll not use some of those, but I just keep them here to avoid any further problem. But of course, you can just comment them if you want. Next, you have the class declaration. The good thing about the compiled version of the libraries or the built-in modules about the boundary condition or whatever it is, you can find a very good commenting on them. For example, here it's a class declaration, private data, origin, axis, axial velocity, radial velocity, omega, and tangential velocity. These were the private variables, as you can see here. And then you have the public section or public variables. As we have seen in our initial file, we need a max here in our variables, and also the maximum radius of the pipe. So basically we need another two variables here that should be defined. In this tutorial, I do not need variables like axial velocity, radial velocity, omega, or tangential velocity. I only need a max and r values, so I can comment them with a slash, a star, and a star, a slash at the end of the section that I want commented. So I will add two other variables: a scalar max underline and then semicolon, and then I want radius, which was smaller r. Now I will continue to scroll down to see if anywhere else needed to be changed based on the analogy. Nothing more, I guess. I think I'm already finished the H file. We'll continue with the C file, and when I want to compile it, if I face any problem, then I come back and check the H file again. In the C file, I have something like origin, axis, axial velocity, or radial velocity that comes from the mesh or the geometry itself. We did not use them in the H file, the one like axial velocity, radial, angular, and tangential velocity. So I can also comment them here in the C file. And then omega tangential velocity, and yeah, from the axial to here up to, let me just put it from here because I do not want to include also the comma, and then go to, so I should comment from here up to the relay section of this one, just like this, and then I should add the variables just the previous section. So I have the axis and origin in the C file. Axis and origin is here, and I should add the umax and the radius over there. To do so, I will use the analogy to some extent. For example, here I will copy and paste the origin just like this, and the only thing that I need at the moment is to add umax and radius. So this one is for umax, and umax, I only want to look it up in the boundary condition, so I just keep the lookup variable. I can also make it a bit more easy by just removing the else. So take lookup for umax and then read the values and return it. For the radius, I will do the same, radius, and here is the radius again. I remove the rest, and also I just want to look it up boundary condition that I have defined. When I define all the variables here, so basically it goes for the variables that we have defined this way, that if we have the origin, then the origin will be read from the center face and then the patch also, so it use the mesh and find the center and so on. Another easy way to do so, just like the 0 it has been written here, you can just put the 0 keyword. For example, if I want to show you something similar, you can also define the radius, for example, just like this, and add the 0 over here. That's it. You have defined a variable with the default value of the 0. That's the other way you can use it. So we leave it as it is for the moment, and if we face some problem, we return and change the values to 0. So let's continue to see the other analogies. I have the origin, axis, and so on. I do not need them. I can comment or just simply remove them. So this, and at the end I need this. I use the analogy, so I copy and paste for the two other variables. I remove the very last comma, and then here I have umax and radius. So I copy the umax underlying value and then paste it here, and I need the radius. I copy it and paste it here. Just to remember why we are defining the umax and the radius here is that if we take a look back into the definition, we have a umax and the r value that should be defined there. So the r is the pipe radius and the umax is the maximum velocity center line. So let's continue to see the other analogies. Again, we have the same thing over here. I copy and paste it and remove the very last comma and then comment the next section. Instead of this one, I should add the umax here and then the radius over here, just like the analogy of the previous variables. I have axis underline something, umax underline something. So just keep in mind, you should always use the analogy over there. Now in the member function, we have the t variables. We will need it in the next subtask over here, so I keep it and comment it because it will be used in the next subtask. I only need the variables that I have defined and the location of the r. So what can I do at this step is that just to comment the t file, the t variable in the subtask. So far we have defined the umax and the r, or the pipe radius value. The small capital R should be read from the mesh itself. It's basically based on the location of the geometry or all of the cell, and it can be defined here in this section. So I just do not need anything from this section, so I just comment it up to the last section. Now I will define then I will add R, which is the radius that I want to calculate. Where should I read it? I should go through the patch and then find the center face or face center. Just if you look at the analogy, it's just like this one. And then I should minus the value from the origin or the center of the jump face. Don't forget to put the semicolon at the end. Now I will define a scalar to calculate the magnitude of R value. So mag R is the name of the variable, and the initial or the value of the variable can define as the function of the magnitude of R value. So this is the built-in function, just like mag, which returns the magnitude of the R value here. And I define the variable called magR to save this value in and use in future. So I put the semicolon again at the end of the line. Next, I should calculate the velocity. Scalar field, I call it parabolic velocity, equal to u max underline, just like u max underline multiplied by 1 minus SQR for S square of the mag R over the radius variable, radius under variable, and just don't forget to add the semicolon at the end of the line. Now I should just normalize the axis. I will define it as a vector. The variable called normalized axis equal to axis underline over the magnitude of the axis. We just normalize the axis using the variable by dividing into the magnitude. And as the last line, just like we had here, I just copy and paste it. So far we just defined components for the final formula, and here I want to define the formula. First, let's remove everything. Here I need the parabolic velocity, which multiplies by normalized axis, and that's it. That's the final formula that I need. Let's check the rest of the file to see if there's anything else changed. I will only keep this fixed value fepatch file here. So what we had here so far was first defining radial or the distance from the center. So we defined a value over here, and then we calculate the magnitude of the R using the function called mag. The CF here, as I said, showed the center faces for each cell, or the cell, the face that located at the boundary. Origin returns the location from the center of face, and then the parabolic profile can be defined as u max multiply 1 minus S square of mag R over the radius. The radius comes from the boundary itself, the file that we defined in 0 folder. And then we apply the velocity along the flow axis. So we use the normalized axis here, and then we multiplied them to have the velocity profile for the face. There's a right function here, and also here, that shows the boundary condition parameters should be written to the disk when OpenFoam saved data files. And then we have runtime selection table entry over here that registers the class in the OpenFoam runtime system, so it can be recognized when specified in the boundary field. Now let's compile it to see if we receive error in between. Probably yes, we will. Just wclean first and then wmake. So the first thing is that the vector was not declared in the scope. That's true. It's vector, so I should t here. It was a typo, so I recompile it. There's also other errors, so I just want to show to solve them one by one. The next one is the axial velocity was not declared in this scope. Where is it? Let's see. Where is the axial velocity that have been used? In the C file, as you see, line 256, the axial velocity here, they will be written. So I will just comment these parts also up to here, and instead of these values I will add the umax axis is already here, so only the umax and the radius. So I will paste the radius and umax here. Just remember to add the variable also after the radius. Now let's compile it again. There is still one error. Let me just first clear the terminal, w clean first, and then w make. Let's go from the top to start. It says that the lookup cannot convert from the IT stream to the scalar. So let's go back to the section parabolic velocity FV patch field vector field.c file. So we are in the right file, and then we should find the dict lookup from IT stream. So problem looks like to be here. Let me just put it as I said before, just define them as the origin axis you marked. One thing is that they should be a scalar, as it said here. It cannot be converted to the foam.scalar because it's now IT stream. I copy and paste them from before, so I only need to add their type, which is a scalar, both for umax and radius. Now let's clean the terminal by the clear command, and then w clean to remove any uncompiled version there, and then compile it using w make. Now let's wait for the other problems to see. Go back to the top. Here I have the s square multiplied by something. This multiplication shouldn't be there because the sqr is a function, so it's just right here in the parabolic velocity variable. Let's save it again. Clear, w clean, and w make. Now waiting for the compilation. So it's successfully compiled, and then we should try it in a simulation case. So I have already defined a 2D simulation case. I want to use it here. We can find it on my website. I put the link in the description below, then you can easily download it. So let's first put it into our directory. Now I put it into my directory case, and I have this case parabolic velocity that I have already defined. You have the mesh, system 0 and constant folders. In the control dicts you should include the library name, which is parabolic velocity, where you can find the name is here. When you compile it, you have the name. You should start from the very letter after the lib and up to the .so. So you will paste it here. Now let's first compile or build the mesh. I open a terminal again here. First I overload the OpenFoam 12 as I have defined the alias, then run the simulation. In the folder I also have the fixed value. Let's imagine at the boundary I have a fixed value for the whole patch, and then I have the parabolic, the one we have already defined and compiled in this tutorial. So it's better to compare these two cases together. First I will start to simulate. The mesh is already created, so I will not do it right now, but if you want to have the mesh, you can just copy and paste the 2D pipe mesh and run fluent to fluent mesh to foam. If you do so, you need to give it a name to the online pipe mesh. So the mesh is created. Let's take a look to it by parafoam. This is a 2D pipe, and we should have a parabolic velocity in the beginning or at the inlet. In the 0 folder I have the u variable in the UI use the parabolic velocity type of boundary condition. I give it a value of 2 for u max, radius, the origin, the axis, and the value, which is something like a placeholder we do not use. But as you can see here, all the variables are defined. Then I will go to run it using the foam run. Let me open a new terminal. I don't think it will be run with this, but the solver that have been used here is the OpenFoam. So I directly use the OpenFoam to start the simulation. It says that the parabolic velocity is not defined. It's the name used here. So let's take a closer look to find the problem. And in the control dict, I have parabolic. Let's take a look back into code. I guess I should have here. Yeah, since I use this lib here, just like what have been compiled, I should copy and paste the full name, but I will just remove the lib from here and recompile it. Clean and wmain. There was a lib keyword here that should be removed. And now I will see if I can now simulate it. Yes, it's to simulate it. And the simulation has been done. I reload the case and check the U values. 0 time step. The other the other simulation is not loaded. The other time steps, I mean. So I just close it and reopen the Paraform to see if the problem will be solved. Otherwise, we just open the ParaView itself. So now we have the times. I load the U and let's have the edges and move on. As you can see, the parabolic velocity can be clearly visible here. Since we only defined this boundary condition at the inlet, let me just load the inlet and remove all the other patches and walls and take a close look into it. Let's just load it with the ParaView itself. I'll open and parabolic velocity.foam. If we take a closer look into it and turn off the lighting inspector, yeah, at the center we have a high value, exactly the value that we have defined in the U boundary condition. The U max 2 and the radius is 0.5. So as we get far from the center point, the velocity will be decreased. So we have a fully developed profile at the inlet. The next simulation that we can take care of is the fixed boundary condition, just to compare these two. So I go back to my defined cases. I open a new terminal, load the OpenFoam 12, and then run it using the OpenFoam. I open case fixed value, and then light inspector can be turned off. And now I only want to have the inlet path. Now we can select the U, and then again let's look the inlet mesh just to see there is a difference in the velocity distribution at the inlet. I can show the value between the lowest and highest. Let me check what is the initial. Yeah, let's be 2, and then the clean case, or just simply remove the time folders from 1 to 50. Now let's resimulate it and then reload the file in the ParaView. So fixed value should be reload, and now as you can see, the inlet value for this case a fixed value of 2 meters per second, and the other one is a parabolic value. Let's take a look into the whole case. In the first time step, in the second and third, and at the very last time step, we can clearly see the difference between the two models. So what is the next? The next step is to also include time into the simulation. I will only do the first and the second subtask and let you to do the rest and ask question in the comment section if you need help. So I will just continue with the next one. Let's go back to copy and paste the previous case that I had and start to develop the simulation. I will just close all the terminals and copy and paste the previously developed code and name it parabolic velocity time dependent. Copy and paste the name so I can use it to rename the files over here. Rename and also rename the H file. I go to make folder, files, rename it to the parabolic, time dependent, and read the C file. Let me close this one also and open the option file. Here I will have all the libraries I used so far, so I do not change anything here in the option files. I close it, I go back to parabolic, velocity, time dependent, C and H file. So I open them and as before I choose the find and replace. I put here and I want to change all the parabolic velocity to parabolic time dependent velocity. I click the replace all here, save it and do the same thing here and save it. What I need in this development again is the umax multiplied by the 1 minus square of r2 over r. But here the umax is a function of time which needs a u0 plus a sinus omega t. So I need a couple of variables that can handle the equation. For example, I need a, u0 and omega. So see what we should change here is to go back to the C file and then start to look and define the variables that we need. So I do not the umax anymore, instead I need a u0. Or before changing the C file, let's go to the H file to define the variables itself. So here I define the umax and radius. I should change it to the u0. Why? Because the umax will be changed based on time and u0. So I should define three variables here, a, omega and u0. So let's put u0 instead of umax and then all variable and omega variable. Let's see if I have any other variable that should be changed in the H file. So nothing else, I guess. Let's go back to the C file. Here instead of umax I put u0 and u0 here. I also have defined two other variables called a variable and omega. I defined them also here. They're all scalar, so nothing should be changed. Omega and here also omega into two quotation. Let's continue. Here again I have the umax. I should make u0 and also define a variable and also omega variable. I copied and pasted the line umax and then change the values from umax or u0 to omega and a on the line. So let's continue again. Here I have the u0 instead of umax and I copy and paste this line twice and then add a variable just like the previous line and also the omega. Here in the formulation, what should be changed? First thing that needs to be changed is the umax. So I will define the umax before this line. Umax is equal to the equation. Something before to change it here. If you remember, we had the time. We keep it as comment. So now I have the time in my development case. I cut the line to paste it and keep it close to other lines of my development. So I read the time here and save it in the t variable. I want to use it in the umax. It doesn't need to have the underline here, but the formula was u0 plus a multiplied by sinus omega multiplied by time. If we want to have this formulation for umax, we need to have the u0 and plus a and so on. So let's first put u0 underline plus a multiplied by a underline multiplied by sinus function, and then omega underline multiplied by time. So far so good. And now we want to define the parabolic velocity time dependent. The only thing that I need to change is the umax underline to umax. That's it, nothing else. The rest of the code above is similar to what we had in the previous development case, and then the operator do the same thing here, and we continue to do the right function changes. So I have the u0. What else? I have the a variable and of course omega. Save the file. Let's check the other lines, nothing else. So I open the terminal here in my simulation case and name and call the OpenFoam 12. W clean first to clean the previous compiled version. As you have seen, the ln include folder has been removed from the directory, and then use the wmake to compile the new version and waiting for the compilation to see if any error comes up. Yes, there's some errors. It's called in the C file line 251. 251 says umax is u0 underline. So let's read the error in more detail. So let's see where the problem is. All the new variables defined just like the previous ones, so nothing should be the problem here. Let me go back to the line. U underline omega multiplied by, yeah, the umax is not a field value and it's only a scalar value. Let me recompile it, see if any other errors comes up. It has been compiled by some warnings. The first one is the parabolic velocity time dependent batch vector.h file, line 112. So let's go to the line 112. In the h file, we have defined the new variables just like before, and the problem, the order of initialization is a bit off. So as it suggests, that will be initialized after. So I try to reorder them as a u0 and then a omega and finally radius value. So let's the first w clean the compiled case, clear screen, and then wmake. Now it has been compiled without any warnings or errors. The next thing is to use the parabolic velocity time dependent library into my simulation. I just copy the name of the library, go back to the examples, and I have case parabolic velocity time dependent. First, let's load the library. As you can see, the name is here. I can copy and paste it again. Nothing changed. So by this libs parenthesis the name of library in, I load the library into my simulation, and then by going to the 0 folder, I will define the inlet conditions like the u0, a, omega, radius, origin, and axis, and the value with a placeholder. So I defined all these. I go to run the simulation. Let's open a new terminal. Let's see if the geometry has been compiled or created. Fluent. Let's load the OpenFoam 12 and then Fluent mesh. Into the mesh folder, we have the 2D pipeline. So the geometry is created. I run the simulation using the IcoFoam. It is started to simulate, and then I open the ParaView, open the time dependent case, and also open the parabolic velocity to see all them in the same screen and notice differences, and then the fixed value. Okay, and now I divide it 3 sections. In the first one, I will use the apply that fixed value, and then in the middle one, I use the parabolic velocity, and in the last one, I show the parabolic velocity time dependent, and in all of them, I use the u value and turn the light inspector. Uncheck the light kit. It's totally optional and based on your own taste. Here should be U. And now you can see in the very first time step, they are different. Let me run the cases. Zoom a bit in. All the velocities are from 0 to 2.5 meter per second. And then I run the simulation. As you can see, it's totally periodic value and change with time. We can also take a look to the inlet value. So let me just uncheck the internal mesh and only keep the inlet value. This is for fixed value. This is for the parabolic velocity. And the third one is for parabolic time dependent. As you can see, the three of them are different from each other. Bring it to the middle and zoom a bit in. Let's go to second 27. Again, they are a bit different, although the Umax is the same. So what is the difference between them? The first one is totally fixed value. The second one is the location varied velocity. And the third one is the location plus time dependent velocity boundary condition. As I said, you can find all the simulation files on my blog, and the address is the caption, and you can find what we have seen here in this session here in Introduction to Programming in OpenFoam 12 posts. Also, you can take a look into the other videos and posts. For example, how to create a CFD mesh from a CT scanned rock image. This one is also a nice tutorial. And that was it for this session. You can scroll down into the post, find the download link for the simulation case. Now I mentioned all I wanted to say in this session. Next, we'll go to define a scalar transport into our solver and have a scalar value coupled with the momentum equation. Thank you for being here and happy simulation.